Hello everyone, this is the third video of the vulnerability research on the Linksys E1200 version 2 wireless router. In this video, I will be walking through the steps we can take to interact with the printed circuit board or PCB of the device and provide ourselves with a remote shell. So, to quickly recap what we have covered in the previous video, we went through the OSINT techniques to uncover data available online such as SCC images of the PCB, known CVEs, and other useful information that all can be found online without access to the physical device. So this forms the information gathering phase of our pen testing workflow. For this walkthrough, I will be using the digital multimeter. Over here, you can see 3 jumper wires. Over here are different colors for identification. A USB to TTL adapter that will be attached to the jumper wires, and access to the printed circuit board of the device itself, as you can see over here. Also, I'll be using the Raspberry Pi 5 over here, you can see, to connect to the device using the USB to TTL adapter. Alright, however, you can use any device with a USB port instead, right? Okay, so first, we have to identify the ground points on the device. By looking at the PCB, we can identify a few potential candidates. So let's take a look. So this is the PCB of our device. So from here, we can see 4 potential candidates for the ground points, which are these 2 over here, this metal shield, and this large component connected to a shield on the right, sorry. Okay, so first, it is important to note that we should never use the continuity mode on a powered board, right? So first, we have to turn the digital multimeter to the continuity mode. This is identified by this label over here, which I will show you on the physical multimeter later on. Next, we will touch both of the probes, which are the black and red probes, on each other, and we should hear a beep sound. This is to confirm that the multimeter is working and ready to test the ground points, right? So next, as mentioned before, we should turn off the power source to the board device or board on device, right? And next, we can identify potential ground points. So these will usually be metal shielded components or any other components with visible silver metal casing, as what we have covered or identified on the printed circuit board. Alright, so now back to the workbench. Now we can start confirming the ground points on the PCB. So as what we have seen before, the potential ground points will be this component on the left, the one on the right, the long shield connected to this particular component, and this shield component itself, right? So there are 4 points that we have identified. Right, so first, we can turn the digital multimeter to the continuity mode as we have identified by the symbol before, right? Next, we will touch the probes, one connected to the COM, another one to this particular port, right? So as you can hear, there will be a beep sound, right? So this confirms that the digital multimeter is working. Next, we have to ensure that the device itself is not connected to any power supply, right? Okay, so now let's start identifying, confirming the ground points, right? So start off with this on the left, right? Okay, now just touch it. No beep, no beep, no beep sound, right? Okay, also here, there's no beep sound. Now when we change over to here and here, you can hear beep sound. Beep, beep sound, right? How about here and here? No beep sound. How about here and here? No beep sound. Alright, so this tells us that these 2 components, this and this component over here, are the ground points, while those on the left and the right, the rings, are not the ground points. Alright, so now that we have identified the ground points on a physical device, we can now use a few methods to find the potential UART interface candidates. So first, we can identify it with potential labels on the hardware itself. So for example, over here, there might be labels such as VCC, GND, RX, and TX, which stands for the voltage power source, ground, receive, and transmit. Or sometimes they might even just put the word UART over there, right? Or visual appearance. So if there are no obvious labels on a device, you can still identify a UART interface by observing the following patterns. This would be 4 to 5 gold-plated hole or oval circular shaped portions aligned in a neat row, such as the image over here, the images over here, right? Looking back at our printed circuit board, we can actually identify it over here. Well, as I mentioned before, 4 to 5 gold-plated rings aligned in a neat row. So as we see later with a clearer image, there are no labels actually to label this particular UART interface, but this is a really dead giveaway of the UART. So following that, we can use a digital multimeter to identify the UART pins by various electrical identifications. Right, so the points here outlines the electrical characteristics of each of the UART pins. So for TX, which stands for transmit, this value will usually fluctuate from 2.5 to 3.3 volts when tested on the multimeter. For RX, it will be fluctuating slightly before, it will fluctuate a little bit before stabilizing at 3.3 volts, given that the particular electrical component or UART uses a 3.3 volt voltage, right? As for the GND, which is ground, it will drop before stabilizing at about 0 volts. And as for the 3.3 volts power source, it will fluctuate slightly before stabilizing at 3.3 volts. However, it is more erratic than the RX, right? However, we will not be using 3.3 volts in our UART shell, only the TX, RX, and ground. So now back to the workbench. Take note that we will test the UART pins, the voltages on the UART pins right after the device is booted up. This means right after the power supply is switched on to the device. So now we have to turn the digital multimeter into the DC voltage mode, identified by this label over here. The black probe will go inside the COM and the red probe will go inside the one on the right. We will place the black probe right here on the ground point, and the red will cycle through each of the UART pins over here, right? So now let's turn on the power supply and start testing. As you can see over here, right, stabilizers at 3.3 volts. While for this, you can see it fluctuates quite a bit, right? For this, stabilizers at 3.3 volts too. Okay, it does not give really any useful readings of the last stabilizers at 0 volts. But let's go back to the second one, which is likely to be the TX, since it fluctuates quite a bit from the range of 2+ volts to 3.3, right? But usually it will stop at the end. Okay. So from the results, we can identify the specific pins on the UART, right? So the most prominent one will be the one from the second from the rightmost, which will be the TX, since the voltage value fluctuates from 2 point something to about 3.3 volts, right? However, the RX, which is the one second most on the left and the first on the right, which is the 3.3 volts power supply. These two are actually quite hard to differentiate, since both of them stabilize just at 3.3 volts, right? However, remember from previous videos that we are able to view an image with identifications of the UART from online sources, right? From here, let's say the second from the rightmost will be the TX, while the rightmost will be 3.3, and the one on the left of the TX will be the RX. As for this, the one which we identify to have a somewhat weird voltage reading can be ignored, and the one on the leftmost with the stable 0 volts will be the ground, right? Also, another method we can actually use to give us more confidence of the RX pin to differentiate it from the 3.3 volts will be this little, can you see this little bus connection, which are only connected to the RX and the TX, which will then lead to the other electrical components on the PCB. Therefore, only the RX will be the one, since it requires communications to CPU and other components, will it be connected via the bus, while the one on the right with a little bit of a different, what I say is a little bit different looks, is likely to be the 3.3 volts. Okay, so now that we have identified the UART pins, we can start interfacing with the device. So for that, as mentioned before, we will have to use the 3 jumper wires connected to USB TTL adapter. Okay, let's give it some time for it to focus. Sorry about that. Okay, yes, it's focused. So as you can see, there will be labels on the right side over here. 3v3 at the top, TXD, and RXD, followed by GND. Right. So for that, we'll be connecting the ground to the ground point on the device. The TXD, which is transmit from the USB TTL into the RX and the RX to TX respectively. And also, as mentioned before, I'll be using the Raspberry Pi, where I will connect the USB from the USB TTL adapter directly into my Raspberry Pi, and I will have a shell console on my Raspberry Pi to interface with the device. And also take a look at the setup I have now, where the USB TTL adapter is connected to the Raspberry Pi, with jumper wires connecting directly to UART pins, right? Remember, TX to RX and RX to TX respectively between the Raspberry Pi and the device. Let's take a look at the screen. Right. So we will be using the Picocom command with the B flag along with the identification of the device that we want to connect to. Now let's take a look at the terminal. Right. So first we have to identify the so as you can see, TTY USB 0. This will be the USB that we are connected, that is directly connected currently physically to the Raspberry Pi. So the Picocom command B stands for the baud rate, right? So what's baud rate? So BAUD rate, basically the rate at which information is transferred in a communication channel. So basically in our case, we have to ensure that this value is valid and is exact in order for us to correctly read the data coming in from the UART interface, right? So we have identified that it is 115,200. However, this value can range from about 9,600 until a very large number, right? However, in our case, we will skip the step of actually identifying this and just go along with this value, as I have found this to work, right? So now we are specify a particular device over here, baud rate, and we have to use sudo, right? Because this is a privileged command. We run it, and now we can see that this output over here. And right after we turn on the power switch to the device, we should see a bunch of values coming on. And because our baud rate is correct and valid, we should see non-gibberish text, right? Okay, so let's check that the power supply is plugged in, our jumper wire is connected, and turn it on. Right, so you can see a bunch of valid and readable text comes on screen, right? So all this shows the boot log, bunch of commands being ran, for example, a bunch of stuff. This is actually very useful for us in the pen testing, for us to actually pen test and research on this product, on this device. But anyway, so after a while, we should eventually see an opening where we can press enter. Yes, hit enter to continue. Sorry, there's text again. Hit enter to continue. where we should be able to retrieve a root shell, right? ID, GID 0, and we are root on the building shell MSH, which appears to be BusyBox, right? We can echo our current shell, and we are bin sh. So from here, we can then perform further system enumeration to identify flaws, weak credentials, etc. to assist us in our pen testing workflow. Okay, so with this, we can conclude the part on hardware interactions and UART shells. In the next video, we will perform further system enumeration from this shell access.